today's class, we want to talk about alkynes. Now, we're going to be focusing on two major reactions of alkynes. And the first one is going to be formation of a metal salts with terminal alkynes. Okay, so in this video, I'm going to be explaining to us the difference between internal alkynes and of course terminal alkynes. And the next one we have addition reactions. All right, addition reactions is peculiar to compounds that possess either a double bond or a triple bond. Okay, so under addition reactions, these are the four reagents. The first one we have hydrogen, halogen halide, and water. Okay, so we're going to be looking at the first one, formation of metal salts with terminal alkynes. Now, let's look at this formation alkynes. Now, the first thing we need to do is for us to be able to differentiate between terminal alkynes and internal alkynes. Right? So you actually understand why they use the word terminal. Now, I'll give us an example after which I'm going to explain. Now we have Now look at this. We have three examples here. The first two examples is under terminal, and the next guy is under internal. Now terminal alkynes, as the name implies, terminal, it simply means that one of the carbons of either of the carbons of the triple bond is having hydrogen. As the name implies, terminal, so that means the triple bond is at the extreme, that is at the terminal. And for this triple bond to be at the extreme, at least one of these carbon of the triple bond must have hydrogen. Right? Now in this case now, this carbon is the one having hydrogen, so this is a terminal alkynes. In this case now, both carbons are having just hydrogen. So you could define terminal alkynes as alkynes in which either of the carbons of the triple bonds are having hydrogen. Either of them occupying hydrogen. It could be two of them, it could just be one. But in the case of internal, as the name implies internal, the two carbons of the triple bond are in between carbons. Alright? So if you look at this guy, these are the two carbons of the triple bonds. Now these two carbons are held or are sandwiched by these two other carbons. However, in this case now, these are the terminals, the extremes. Both carbons are terminals, but in this case now, just one of them is terminal, which actually is enough for this guy to be called a terminal alkynes. Alright, so since we've seen what a terminal alkynes is, like I said, a terminal alkynes can be defined as an alkynes in which either of the carbons of the double bond is having or occupying hydrogen. An example of such is what we have here. Okay, so now let's look at the next stuff. Class, a terminal alkyne is considered to be weakly acidic. Right? Why do we say so? Because an acid is any substance that can donate hydrogen. For example, if I have HCl, I consider HCl an acid because it can give us H plus and Cl minus. So this guy is an acid. Alright? Now, using that concept, a terminal alkyne is basically an alkynes, right? In which either of the carbon of the triple bond is having hydrogen. So the hydrogen of a terminal alkynes, like the hydrogen on that terminal carbon, is acidic in nature, in the sense that it can be donated. Right? So this can actually, when reacted with a strong base, if I react this guy with a strong base, not our normal NaOH. No, yes, this is a base, but not strong enough to react with this. This guy is weakly acidic. So for me to actually, see the acidic properties of this guy, I need to use a base that is extremely very, very strong because this guy is weakly acidic. So that base, we have sodium amide. Example of such base, we have sodium amide and potassium amide. So when you react this guy with this is what is going to happen. We have CH3C. Now, this H has been pulled out to form ammonia with this NH2. Now, this K is now what is going to come here. So this becomes potassium acetylide. Potassium acetylide. If I had used sodium, it would have been sodium acetylide. Right? So the general name for this, you can just use acetylide, irrespective of whether this guy is 3 carbon, 2 carbon, or a single carbon, or 4 carbons. Acetylide simply refers to as, it's a general name for a compound that is formed when a terminal alkynes have lost its proton, or one of its proton. All right, since we have seen what a terminal alkyne is, at least you understand what this means, right? Now, this metal salt, this is a metal salt. This. Now, what is a salt? HCl, NaCl. A salt is a compound that is formed when the hydrogen ion of an acid is replaced with a metal. When a hydrogen ion of an acid is replaced with a metal completely, you have a salt. So when this Na replaces this H, you have NaCl, which is a pure salt. Now, in the case of this is a terminal alkynes. This is actually the hydrogen, right? Now, the base you're going to use to remove this H is going to be extremely strong base, either of sodium amide or potassium amide. And when you use any one of this H will be pulled out, right? And in turn, either of this metal, either sodium or potassium, replaces the H. In this case, I use potassium amide, so it was the high potassium that replaced this guy. So this guy now becomes potassium acetylide. Do you understand? So the reason why we said metal salts is because when you react a terminal alkynes with a strong base, right, you're going to have a metal salt. It is only terminal alkynes that can do that. Internal alkyne, for example, cannot do that. This hydrogen is not acidic, it's 3, right? There is no hydrogen on the 2 carbons of the triple bond. So this guy cannot undergo this reaction. Okay, so let's look at an example. So let's look at one reaction in which terminal alkynes will react with a very strong base. Remember I said the type of strong base that can actually form a metal salt with terminal alkynes are sodium amide or potassium amide. But they may not really ask you that in exams, all right? But let me just give us an example. We have CH3, CH plus sodium amide. So this becomes ammonia. All right, so this is a metal salt. So that is a metal salt. Okay. Now, having said this, the next important stuff I would really like to tell us is the test to distinguish between a terminal alkynes and internal alkynes. Now, how can we distinguish between which alkyne is terminal and which of them is? When you see an alkyne, they will not definitely write on it, this is a terminal alkyne or this is not a terminal alkyne. Right? So when we subject it to a test, it's because a test will enable us to actually tell which of them will test positive or which of them will test negative. Every test comes with observation, and obviously after observing you can draw your conclusion. All right, so now I'll say test to distinguish terminal alkynes from internal alkynes. So what kind of tests can we use to distinguish a terminal alkynes to this? So let's put down. All right, so I'll say terminal alkynes gives a positive test when reacted with alkaline solution of ammonical silver 1. This is silver 1 solution or copper 1 solution. Okay, now full stop. With this solution, A terminal alkynes will give a precipitate, white, a precipitate. However, if you react this guy with internal alkynes, it's not going to give us a precipitate. That means that when you react a terminal alkynes with ammonical solution of copper 1 or copper 2, you're going to get a precipitate. But if you do that with internal alkynes, you're not going to get your precipitate. I'll say alkaline Now, if I replace this, if I say alkaline, copper 1, solution. Now, ammonical, this becomes now these are the reagents. Just in case of exams, they decide not to use the name and they decide to use the formulas. So when you react this or this with a terminal alkynes, these metals will place that hydrogen that I said is acidic to form a precipitate, that is the salt. And one important thing I would like us to know is that these two metals, all right, note, these metals, Ag plus and Cu plus, are the only two metals. This is silver 1 ion, this is copper 1 ion. These are the two metals that can be used to distinguish or that can be used to test for terminal alkynes. Right? Now last year or some years back, they asked a question. They said Ag plus Na plus Cu plus. They now said which of these can be used to test for terminal alkynes? Class, listen. It's only these two in here, because if you use this sodium, you're not going to get a precipitate. And if you do not get a precipitate, that is not a test, because a test is something that you're going to observe a substance and then make your inference. These two metals are heavy metals compared to this guy. So whenever silver or copper combines with a terminal alkynes, it forms a precipitate that deposit at the bottom, and then you can see the color. So once you see the formation of a precipitate, you can now conclude, oh, for this thing to have formed precipitate, it means that these terminal alkynes reacted. So the only metals, the two metals that will react with terminal alkynes is this and this. So in case you see something like this, it is wrong. Okay? Example, we have CH3 plus now this becomes right, now this is terminal alkynes. We have the next one. Now there is no reaction. Now this is a terminal alkyne. So whenever terminal alkynes react with either of this or this, you're going to have this hydrogen replaced with this metal, depending on which one I used. If I had used this one, this copper would have replaced this H. What I would have formed would have still been a precipitate. However, they proceeded to use internal alkynes. Now if you look at these internal alkynes, the two carbons of the triple bond does not have any hydrogen. That is why it is called internal. And not just that, If you look at the position of this triple bond is at the middle, in between two other carbons. But if you look at this guy, this is at the extreme terminal, right? So these two carbons of the triple bond are in between two carbons. That is why it is called internal. And it does not have this hydrogen that will act as an acidic hydrogen. So therefore, no reaction. Take note that this particular guy, this first one, can also be called Tollin's reagent in case of exams. Tollin's reagent, you may ask you, terminal alkynes test positive for Tollin's reagent. The answer is yes. Because if you use any of this to test for terminal alkynes, it will test positive. Okay, so another name for alkaline solution of ammonical silver 1 ion solution, silver 1 solution, alkaline solution of ammonical silver 1 ion, sorry, it's meant to be silver 1 ion. Now this is also known as Tollin's reagent. All right, this one doesn't really have a common name like the first one, so that is it for the first reactions of alkynes. So let's look at the next reactions of alkynes, addition reaction. Okay, so the next reaction I want to look at is addition reaction. Now one thing you need to understand is that anytime we are talking about addition reaction, it simply means that you're adding something to that particular guy. Let's say if we say addition reactions of alkynes, we are adding something to alkynes. Addition reactions of alkenes, we are adding something to alkenes. Do you understand? So addition reaction is basically a case where an atom or group of atoms are added across a multiple bond. It could either be a double bond or a triple bond. So a compound that does not have a double bond or a triple bond cannot undergo addition reaction. Read my lips, cannot undergo addition reaction. Addition reaction is designed specifically for compounds that contains either a double bond or a triple bond, or in general unsaturated compounds, which alkenes fall into the category. Now, the reagents that react with alkynes via addition reaction as follows. We have the first one, hydration, and this guy is halogenation. So we're going to be taking them one after the other. The first one, we're going to take hydrogenation, that is addition of hydrogen halide. Sorry, this is meant to be hydrogen halide. So, but before I proceed, there are things I need us to understand. Now, there is a law or there is a rule. Rules on symmetrical alkenes or alkynes. Now, class, pay attention. Before I proceed to telling us the rule, let's understand what is symmetrical, unsymmetrical, and the rest of them. So we say, now, the reagents in question are these four. These four. Now, what is added to either of these alkenes or alkynes are what we refer to as reagents. So these four reagents, we're going to classify them either as symmetrical or unsymmetrical. And alkynes, I'm going to explain what we mean by unsymmetrical or symmetrical. So you can also apply the concept to alkenes, right? Now listen and listen very carefully. When we say something is symmetrical, for something that is symmetrical simply means that thing has a plane of symmetry. If you cut it into two, you're going to have two equal sides, right? That is symmetrical. For something that is unsymmetrical, when you divide it into two, you're going to have two unequal sides. For example, if I have CH3, C, Now look at the first compound. This is unsymmetrical. Look at the 2 carbons of the triple bond. I placed asterisks on each of them. These 2 carbons of the triple bond, they are not symmetrical because this carbon is having hydrogen, whereas this guy is not having any hydrogen. So we use a number of hydrogens on each carbon of the triple bond to decide whether they are symmetrical or not. So if you look at this first compound, the 2 carbons of the triple bond, what can you say about that? The first carbon has 1 hydrogen, the second guy does not have any hydrogen. So in terms of symmetry, this guy is unsymmetrical because the 2 carbons are not having equal number of hydrogen. This is having 1 H and this guy is having no H, so they are not the same. If you cut this triple bond into 2, what you're going to have on the right hand side will not be the same as what you're going to have on the left hand side. So that's the concept of symmetry and non-symmetrical. Now if you look at the second compound, the 2 carbons, this compound is symmetrical because if you look at the 2 carbons of the triple bond, this guy is not having any hydrogen and this guy is not having any hydrogen. So if you split this guy into 2, you're going to have equal parts. The left hand side will be the same thing as what we have on the right hand side. Can you see that clearly? So if you come here, you cut this into 2. This carbon here is not having any hydrogen. This carbon here is not having any hydrogen. So this guy is symmetrical. So the concept of symmetrical alkanes or alkynes is basically dependent on whether the 2 carbons of the triple bond, that's for alkynes, or the 2 carbons of the double bonds, that's for alkenes, are they having equal number of hydrogens on both carbons? If they're having equal number of hydrogens, they are symmetrical. If they are having unequal number of hydrogen, they are unsymmetrical. If you look at this guy, this is symmetrical. Yes, there is no hydrogen here, but the same thing is actually seen on both sides, right? So this has no hydrogen, 0 hydrogen. This guy has 0 hydrogen, so both sides no hydrogen, so they are symmetrical. This has 0 hydrogen, 1 hydrogen. They are unsymmetrical because they do not have same number of hydrogens on both sides. Okay, so having explained that, now let's look at reagents. Now amongst these 4 reagents, if you look at this, H, X, H2O, H2, X2. Now look up. Now if you split this guy into 2, what you're going to have on both sides are not the same. Hydrogen will be on the left, halogen, which is X. Do not forget that this X can either be fluorine, chlorine, bromine, or iodine. So when we say X, we are not referring to the the 10 letter Roman figure, be Roman numeral. We are using X represents those guys. So if you look at this, the unsymmetrical is HX and H2O, and the symmetrical is this and this. Now why do we call this HX unsymmetrical? Because if you split this guy into 2, you're going to have H plus and X minus. What we have on both sides, they are not equal. One side is H, the other side is X. They are not the same thing. So if you split this guy, you're not going to have 2 same species on both sides, so they are not symmetrical. Symmetrical is something that when you split it into 2, what you have on the left hand side is equal to what you have on the right hand side. But in the case that after splitting it into 2, what you have on the left is not equal to what you have on the right, that is unsymmetrical. All right, so this guy is unsymmetrical because if you split this guy, you're not going to have same thing on both sides. Now water is H. Now this is how water splits. Water splits as H and OH. So one side is going to be H and the other side is going to be OH. So water itself is unsymmetrical as well. Do not forget that. Water is unsymmetrical. Now, what are the symmetrical reagents? The hydrogen. If you split this guy, this is H. If you split this, you're having H and H. It's very obvious. Both sides, you're having same thing on both sides. You split this, you have two things on the same, both stuff on both sides, same thing on both sides. That's symmetrical. You come here, X2. If you split this, you have same thing on both sides. So now that we have understood what unsymmetrical alkenes or alkynes are, and we understood what unsymmetrical reagents and symmetrical reagents are. Now look up. We said the rule guiding addition of unsymmetrical reagents to an unsymmetrical alkene is called Markovnikov rule. It's called Markovnikov rule. I already explained to us what unsymmetrical reagents, unsymmetrical alkynes, and vice versa. I already explained that. Now, what does this Markovnikov rule state? It states that during the addition, the hydrogen of the reagent will add to the carbon of the double bond. That is if it was an alkene. But since we are talking about alkynes, I'll say we'll add to the carbon of the triple bond with more hydrogen. For example, the two unsymmetrical reagents, example of unsymmetrical reagents is we have water and hydrogen halide. I already told us this. Okay, and I already gave us example of unsymmetrical alkyne. Let's say we have CH3. Let's say we have something like this. So we'll say CH3 plus HBr. Now once you see this HBr, this Br, remember it falls under the X. X I say can be F, Cl, Br or I. So this Br, the two atom here is H and Br, and the two carbon of the triple bond is here. So this is carbon 1, carbon 2 and carbon 3. The two carbons of the triple bond are carbon 1 and carbon 2. If you look at them, they are unsymmetrical. Carbon 1 has one hydrogen, carbon 2 has no hydrogen. It simply means that if you actually add this, we have H and we have Br. So this H, between these two carbons, which of them would the H go to? The rule says, in this case, the hydrogen goes to the carbon of the double bond that has more hydrogen. Carbon 1 has one hydrogen, carbon 2 has no hydrogen. So it means that carbon 1 has more hydrogen, so this hydrogen from this HBr will add up to this carbon 1. So this becomes CH3. Please, you can put a bond here. This bond, when you do that, this triple bond reduces to double bond. This initially had one hydrogen, but when this H from this HBr adds here, it becomes CH2. So let me just put it up. And then this Br, we have something like this. So if you write this, this now becomes CH3 so this is what we have. Now what if in the case of water? We're going to come to that. So if I have CH okay, so this is what we're going to have. H comes to here, this comes to this. If I have something like this, if you notice, this alkynes is symmetrical. This is symmetrical. It means that the two carbons of the triple bond do not have any hydrogen. If you divide this into two, you're going to have something on both sides, right? So it means that since this guy is symmetrical and this guy is unsymmetrical, once any one of them is symmetrical, there is no rule. No rule is going to guide it. It means that this H can either add to this carbon or to this other one. Any of the carbon that it chooses to add to, it doesn't really matter. Do you understand? All right. Now, one last thing I would like to tell us is that It's only the two carbons of the double bond or the two carbons of the triple bond that we are interested in. Whatever I have on this other side is only the two carbons of the double bond that we are interested in. We have no business with other carbons. All right, so let's solve this guy. This is unsymmetrical because these two carbons of the triple bond, they are having an equal number of hydrogens. H will come to this, I comes to this, so this becomes CH3 C CH. If you add another hydrogen here, it becomes 2. This is what we have. In this case now, you can add the H to any side of your choice. Okay, so that is it. Now there is also what we call anti-Markovnikov rule. Now there's also what we call anti-Markovnikov rule. Now what is anti-Markovnikov rule? Anti-Markovnikov rule is the opposite of Markovnikov. In Markovnikov, the hydrogen goes to the carbon of the triple bond or carbon of the double bond that has more hydrogen. In the case of anti-Markovnikov, the reverse will be the case. So for Markovnikov, for anti, I'll say hydrogen of the reagents goes to the carbon of triple bond or double bond with less hydrogen. But the question is, how would I know when to apply anti-Markovnikov? In the case of Markovnikov, it is normal. Once they give you this and this, right? You just know it's Markovnikov. But anti-Markovnikov, they must actually indicate something for you to know that it is anti-Markovnikov. So that stuff, please take note. Anti-Markovnikov takes place only in the presence of peroxide. It takes place only in the presence of peroxide. So like I repeat, I said anti-Markovnikov only takes place in the presence of peroxide, whereas Markovnikov rule doesn't need a peroxide. Once the reagent and the alkyne is unsymmetrical, Markovnikov rule takes place, right? But once there is a peroxide indicated, it's going to follow anti-Markovnikov. So for Markovnikov, the reagents and the alkynes has to be unsymmetrical. In anti-Markovnikov, it also has to be unsymmetrical. The only difference is that in Markovnikov, no peroxide. In anti-Markovnikov, there is peroxide. So the peroxide can be written like this, or the common peroxide is hydrogen peroxide, and the next one is methyl peroxide. This is a common peroxide, which can be written as CH3O2. This same reaction, let's repeat it here. We have now we have peroxide. This time around there is peroxide. This is unsymmetrical and this is unsymmetrical, and there is peroxide written here. So that is how they will show it. They could either show it directly like this, or they will say it, they'll give us in terms of words, right? So what you're simply going to do is that if it's in this Markovnikov, H came to carbon 1 because carbon 1 had more hydrogen. Markovnikov says hydrogen goes to the carbon that has more hydrogen, carbon of the triple bond that has more hydrogen. Anti says hydrogen goes to the one that has less hydrogen. All right, so the product of this guy becomes the H goes to the one that has less hydrogen, which is this, and the Br goes to the opposite. So this now becomes CH3, C, so if you write this well, it now becomes CH3, all right, so that is that for peroxide, right? Explanation. So the next thing we are going to do is to look at reaction with other reagents. We've just seen reaction with hydrogen bromide, that is hydrogen halide. So the next one we're going to look at would be we are still under addition reaction of alkynes. We have done addition of HX, where X is F, Cl, Br, or I. So the next one is addition of water, and then we have addition of hydrogen, addition of halogen. So we are done with the first one. So we are left with these three now. All right. So we are done with this. So we want to look at addition of water. Addition of water to alkynes. Now, class, it's important for us to know that water is an unsymmetrical reagent. So as a matter of fact, when water is added to an alkyne that is unsymmetrical, Markovnikov rule is going to be, used. However, if water adds to an alkyne that is symmetrical, no rule. So let's take for example. I'll say, okay, please put down. Let me explain something. Addition of water to an alkyne is a two-step process. Addition of water to an alkyne is a two-step process. The first step would be formation of enol. Enol is basically compounds that contain ene, that is double bond, plus alcohol. That is enol. Okay, formation of enol, compound that contains ene and ol. Now the next one we have, the second step is rearrangement of the enol that is known as tautomerism. Rearrangement of the enol to aldehydes or ketone. Now, note, it will only give us aldehyde. Note, aldehydes if the alkyne it will only give us aldehyde if the alkyne is ethyne. That is, alkyne that contain just two carbon. All right, this is the least member of the alkynes. So if the alkynes is ethyne, the product we're going to get is going to be an aldehyde. Now listen, once you add water to alkynes, it's a two-step process. So the two-step carries on simultaneously. The first step will be formation of enol. The second step will now be rearrangement of the enol to give us an aldehyde or a ketone. A ketone if it is an alkyne other than ethyne. Every other alkyne other than ethyne will give us a ketone, but ethyne is going to give us an aldehyde. So let's look at an example. We have CH3, CH plus water. Now this is propine. Now this propine is unsymmetrical unsymmetrical alkyne. This is water. Unsymmetrical reagent. So remember, anytime unsymmetrical reagent reacts with an unsymmetrical alkyne, Markovnikov rule must actually come into play. Now, this water is splitting as H and OH. So let's look at the reaction. This reaction is always carried out in the presence of mercury salt and an acid. So we have an acid, mostly H2SO4, and a mercury salt. So addition of water to alkyne is always carried out in the presence of an acid and a mercury salt. All right, so mercury salt can be HgSO4. So this shouldn't actually be a problem to you. Just know that when water reacts with an alkyne, right, it is always done using an acid as a catalyst. So acid makes the reaction to occur faster in the presence of a mercury salt. So now, water is H and OH. So the two carbons that will be added, these are the two carbons. The H goes to the carbon that has more hydrogen, and OH goes to the carbon that has less hydrogen. So this becomes CH3, C. Now this is the first product. Now this H goes to this carbon. This carbon was already initially having CH. When another hydrogen adds, it becomes CH2. OH adds to this one. So this is what we have. So this compound is known as propanol, an enol. Why do we call it an enol? Because a compound that contains in a double bond and OL, alcohol. Alcohol functional group is OH. So if you look at this, it contains a double bond. It also contains OH. So that is an enol. So propanol because it contains 3 carbon. So remember, this reaction will not stop here. It's going to rearrange to give us a final product. So this process is called tautomerism. Now, what is tautomerism? Tautomerism is a case where the hydrogen of the OH, right, exchanges for one of these bonds. So this carbon is having CH2. So this is what is going to happen. This H moves away from this OH, add up to this guy to form CH3, and the H, this bond moves away from this and comes to this point. So this becomes CH3, this is it. Tautomerism is basically a process that involves the exchange of a hydrogen and a bond. Hydrogen from the OH interchanges with this guy, here becomes CH3, and this bond comes here becomes a double bond. So this now becomes propanone, which is a ketone. So that's the reaction of that's the product. So let's look at more examples. We have now this is ethyne. This ethyne is symmetrical because the 2 carbons of the triple bond are having equal number of hydrogen. So in this case, Markovnikov rule will not come into play because Markovnikov rule is only applicable when both the alkynes and the reagents, or the alkenes and the reagents, are both unsymmetrical. This guy is symmetrical and this guy is unsymmetrical, so it's not going to work here. Water is H and OH, right? So this becomes the first step. This is H. One of the H comes to one of the first carbon. So this becomes CH2. Class, remember, this guy has a triple bond. When you add something across, the bond reduces from triple bond to double bond. I already explained in the previous example or reaction. So one of these H adds to this, it becomes CH2, which is what we have here. The triple bond reduces to a double bond, and we have CH OH. Now tautomerism will take place. That's the rearrangement. And what is going to happen is that this H from the OH comes to this carbon. Please, this H does not add to the carbon bearing the OH. No, don't forget that the H goes to the carbon on the other side, the adjacent carbon. So this becomes CH3. This bond, one of the bond goes to the O. We now have, so this is now ethanol and aldehyde. Do not forget that this reaction took place in the presence of an acid, usually H2SO4, and mercury salt. Mercury has a symbol of Hg. So if I put HgSO4, this is mercury sulfate, which is a salt. Mercury is a metal. So the reaction, addition of water to alkynes, is usually carried out in the presence of an acid and a mercury salt. So we have CH. Now this is butane. Butane 1-ine plus. Now we have this is H and OH. The two carbons in question, carbon A and carbon B. Now this H, between carbon A and carbon B, which of them has more hydrogen? This is unsymmetrical and this is unsymmetrical. So Markovnikov would be applied. So Markovnikov rule will be applied. H goes to the carbon that has more hydrogen because between these two, this guy has more hydrogen and this OH comes to this side. So this now becomes CH3, CH2, C, OH, CH2. Now this H comes to this, we now have CH2. Now tautomerism will now take place. Now when tautomerism takes place, the H of this OH comes to this other carbon of the double bond and add up to this point and form CH3, while this bond goes here to form a ketone. So this becomes CH3, CH2, so this is now butanone, a ketone. As simple as that. So that is how we know, or that's how we carry out reactions of alkynes with water. All right. All right. So let's look at the next example: reaction of alkynes with hydrogen. Addition of hydrogen to alkyne. That's hydrogenation. All right. Now, hydrogenation reaction is basically addition of hydrogen across. This reaction can take place with an alkenes or an alkynes. Remember, any compound that has a double bond, right, can have atoms or group of atoms being added across the carbons of the double or triple bond. So in the case of alkynes, right, we're going to be adding hydrogen across the multiple bond. Now, hydrogen is a symmetrical reagent in the sense that if you divide it into two, you're going to have H on one side and H on the other side. So that is how it is. All right. Now, so the next thing I'm going to do here, I'll say, what is hydrogenation reaction? Hydrogenation reaction is a case where if you add two atoms, if you add a molecule of hydrogen, one molecule of hydrogen is H2, which comprises of two atoms. So if you add one molecule of hydrogen, right, you're going to remove one of the triple bond and it reduces to a double bond. If you want to remove that double bond again, you add another molecule of hydrogen, you now have, so if I want to move from this, if I add H2, now this is what is going to happen is that these two atoms will add across this and the bond reduces to 2. We have this, we have this. If I add another H2, this other bond goes off. We have this H, 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 and H. So it means that 2 moles of hydrogen molecules is equivalent to 4 atoms of hydrogen. Now what we have here is a clear case of complete hydrogenation of alkynes, where alkynes is reduced to alkanes. Alkynes to alkanes. Alkanes in the sense that there is no double or triple bond. Alkanes are always having a single bond, and alkynes are having a triple bond. Now, however, what if I decide to stop at the alkene stage? Right? So that brings us to the two types of, the two classes of alkynes hydrogenation. I can hydrogenate alkynes and move it from alkynes straight to alkanes, single bond, or I can move it from a triple bond and stop at the double bond. So here, if I stop here, that is partial hydrogenation. If I stop here, that is complete hydrogenation. Now, how do we achieve partial or complete? Depends on the substance we're going to be reacting alongside the hydrogen, right? So let's look at this in details. Hydrogenation of alkynes can be a complete hydrogenation. Now, this place we use catalytic hydrogenation. That is addition of hydrogen, H2, in the presence of nickel, platinum, or palladium catalyst. You add this and use any one of these catalysts, this metal catalyst. The next one is note, complete hydrogenation of alkynes gives alkane. So the B part is partial hydrogenation. Now, partial hydrogenation is simply, stopping at the alkane stage. I don't want to get to the alkane. I want to stop midway, all right? So we have two types. I can decide to stop midway to form a cis alkanes, where the two hydrogens on both carbons are on the same side, or I can have a trans. So let's look at them. The first one is if I use of Lindlar's catalyst. Now, what is Lindlar's catalyst? Lindlar's catalyst is hydrogen in the presence of palladium, but then this catalyst is poisoned with calcium carbonate. So Lindlar's catalyst is basically hydrogen, addition of hydrogen in the presence of partially poisoned palladium catalyst. If you had not put this calcium carbonate, it would have been H2 and palladium, complete hydrogenation. But you poisoned this palladium. Poisoning palladium simply means you will not allow the palladium to carry out its full function. All right, so that is why you have this guy. So this will give us, this gives a cis alkanes, right? If I use Lindlar's catalyst, I'll be getting cis alkane. Now the next one is use of sodium in liquid ammonia. So most times you see it like this, Na, sodium in liquid ammonia, right? Now this gives a trans alkenes, all right? Now let's look at the next one. Partial hydrogenation. Now the first one is to give a cis alkyne. Now I'll use of Lindlar's catalyst. So this becomes CH3 Now this is Lindlar's catalyst. Hydrogen, palladium / calcium carbonate. So this calcium carbonate is actually restricting this palladium to carry out its full responsibility or activity. So this is what I'm going to do. The product of this will simply mean that I'm just reducing this guy from a triple bond to a double bond, which is CH3, C, puts H, and puts H. Remember, we said it's going to give us cis alkene. Cis, like I said, the two hydrogen that will be added would be on the same side. It's either you choose up for both of the hydrogen or you choose down. That is basically what cis means. Right, but you cannot present your answer this way. This is not a cis pattern. This is not how to write cis. If you write it this way, you're correct, but the geometric form of this is not correct. So for me to get the cis and the trans, or the cis of this, I'll say the two carbons of the double bond. I'll put it this way. This is the best way to write cis or trans. This form is a cis form. So I come here on these two carbon, I have H up here. I also have H up here. All right, so this becomes CH3 and CH3. So this is but 2N cis. So this is the final answer for this. So in exams, don't write this. This is what you're going to write. Except the question is in word format. They say which class of geometric isomers would be formed when Lindlar's catalyst reacts with an alkyne. It is a cis isomer. If I react the sodium in liquid ammonia with alkynes, I'll have a trans, right? So that is that for the cis. So first thing first, I gave us the product and then showed us how to write this in a cis form. But in exams, there is no need giving them this, just give them this directly, right? Now let's look at to give trans alkenes. In order for us to give trans alkene, I'll use sodium I'll put sodium in liquid ammonia. Now, first thing first, once you see this, it's basically addition reaction. That hydrogen is added. Ammonia is what is producing the hydrogen. Remember, for us to form ammonia, you react hydrogen with nitrogen. So if you want to actually release back the hydrogen to this, you do this. So the two hydrogen that will be added to this will come from this ammonia. But this time around, it's going to give us a trans, meaning that the two hydrogen that will be added on these two carbons will be on opposite side. All right, so this becomes CH3, C. Now you add H on one side, add this on the other side, and that is a trans. The two hydrogen is added on opposite side. So let's write it in a geometric form. All Alright, so make it look like the real trans. So I'll come here. These are the 2 carbons of the triple double bond. So I'll say this equals to this. So this becomes H, and this becomes H. We have CH3. We have CH3. So this is but 2 in trans, because the 2 hydrogen on both sides are on opposite side. So that is that for addition of hydrogens. Let's look at the last reaction of addition reactions of alkynes, which is addition of halogens. Alright, so let's assume alkynes to be this plus, now this is 1 mole of X2. Now 1 mole of X2 contains 2 atoms. So addition of 1 mole of halogen is going to give us a substituted alkenes, because if you add 1 mole, it's going to reduce the alkynes to an alkene that has a double bond. Alright, if you add another molecule of that halogen, it will now take a double bond to an alkane. So this is what I mean. This becomes you can add this anywhere, doesn't matter. This is a substituted alkenes. It's an alkane that has a substituent. Now, if you add another halogen to that, this becomes alright. So let's look at real example. So we have CH3 plus 2 Br. Now, 2 moles of halogen will convert alkynes to alkanes directly. 1 mole will convert alkynes to alkanes. Now imagine a case where they gave us 2 moles. Now there are 2 options here. It's either you take it step by step to show how the 2 moles are being added, or you do it straight to just arrive at the final answer. So I'll do it using the 2 different ways. So let's do it step by step. So this simply means I'll say solution. I'll say CH3 plus, I'll add the first Br, and my product would be CH3 Br, and then I'll add the next another Br. I'll now remove this other double bond. This becomes CH3 we have this. Now this is actually moving in a stepwise manner. Now what if I had done it directly? Plus 2 Br2. So this becomes CH3. Now this 2 Br means 4 atoms of bromine, right? So this becomes Br. I'm only interested in the 2 carbons where the triple bond was. So I remove the bonds and I put the halogens. So the name of this compound is 1, 2, 3, 4. Parent name is butane. On carbon 2 we have 2, 2, 3, 3. Because this is carbon 2 we have bromine. Carbon 3 we have this tetra bromo butane. This is the same thing as this. Now what of this guy? This one is going to be 1, 2, 3. On carbon 2 and 3 we have bromine. So this is going to be 2, 3 dibromo 4 carbon atom is both. So this guy is for this, while this is for this. Please do well to subscribe and hit the like button. If you have any question, drop it on the comments.